Hello and welcome back, everybody. Moving on to chapter 5. This is the last chapter in the book. We're going to be talking about multivariable integral calculus. And with this first section, going right back to the fundamental theorem, maybe plural theorems, of multivariable calculus. So way back at the beginning of the book, we had our kind of our naive version of this, and it didn't look so great. But I hinted at something called the Generalized Stokes theorem back then. Actually, I did write it down in its full generality, but we didn't really know what any of the terms which are in the Generalized Stokes theorem were actually referring to. And now, I mean, if you went back and looked at it recently, you would find out you do know what a lot of the terms are, and especially we're going to see it again today. You're going to be so much more well prepared to understand what the Generalized Stokes theorem is saying. Now, still in a course like this, you really want a second semester of multivariable calculus, or what a lot of people would probably call differential geometry, or calculus on manifolds or something like that, to really fully prove the Generalized Stokes theorem. But I think we do have enough under our belt that we'll be able to get a pretty good idea of what it says today. So let's talk about that. Let's see maybe where that would come from. We're going to recall that differential forms, right, kind of the beginning of the last chapter, I mean the whole last chapter was differential forms, but the beginning helped us understand that this one-dimensional integral, when I integrate from a minimum value up to a maximum value of a function times dx, we remember that we think about dx as a vector in the x direction of infinitesimal length. And we think about the f that's multiplying that vector just as a scalar. So at every point in space, the vector is scaled. It's scaled by the value of the function, and then we're going to add infinitely many of those, starting at x min and ending at x max. And what's important about what I just referred to, you're going to see this become quite a bit important later. I have this idea of starting somewhere and ending somewhere else. That is the idea that mathematicians will refer to with integrals of differential forms as an orientation of the domain. Okay, so an orientation of a domain is just some sort of directionality. This is like a natural directionality to that domain, in the sense that you could, of course, exchange the directionality and recover a negative. I think everyone remembers something like 1 to 10 of f of x dx is equal to the negative of 10 to 1 of f of x dx. This is one of the earlier kind of theorems you would learn in calculus, is that if you exchange the bounds, you swap the bounds around, you pick up a negative sign. That's the idea of orientation of the domain that you'll see show up now and then. Well, if we want to think about this interpretation of infinitely many, infinitely small vectors that we're going to add all the way together, and each one is scaled by the integrand, we can do that in any number of dimensions, right? Because we know this idea of a differential k-form, which, over here we had a vector, but our k-form is, some version of dx wedge dy wedge dz wedge, dq or something. Who knows where it ends? But, you have all these wedges. This is an infinitesimal. Well, these wedge products were giving us, I guess, at the first stage a parallelogram, at the second stage a parallelepiped, and then all the way up we call these things parallelotopes in any number of dimensions. So these are infinitesimal parallelotopes. So they occupy some sort of k-dimensional space when it's a differential k-form. So each one occupies some sort of k-dimensional space, and you end up summing infinitely many of those. So you're adding infinitely many, infinitely small k-dimensional objects together, and of course what you get out of that, this is the output here will also be a k-dimensional volume of sorts. I'll put volume in quotations because it's not quite volume, but you get the idea, right? We're just, in this case, you could think about adding infinitely many of those vectors together, and you get some sort of distance, which is kind of our one-dimensional volume, which is, or length, which is one-dimensional volume. But in higher dimensions, if we're working with a k-form, we'll pick up this k-dimensional volume as the output. And it's just because we're thinking about adding infinitely many of these infinitely small parallelotopes together. And of course, we saw in differential forms, each of those parallelotopes can be scaled independently by some scalar field. You may be asking, where is the dx in the above when I introduce this multivariable integral? Well, it's kind of baked in here, right? It's when we define a differential form, it's going to look like we don't actually have a differential in there, but that function f is actually defined to output some copies of dx. And so, for example, like this could be a differential form, and you'll see, dx is actually in the output of f. It just isn't clear when you write it in the integral where that dx is. But down here, the output of f has both a dx and a dy inside of it. So that's really where those dx's and dy's are coming from. So what you'll see a lot in multivariable calculus is integrals kind of this form, where you'll be saying that you're integrating over some function that multiplies dx and then another function that multiplies dy. But you really just think about that as integrating the differential one form that is comprised of both a scalar on dx and a scalar on dy. But you can think about that as individually just two individual one-dimensional integrals in the case of differential one forms, because each direction of a differential one form is, of course, one-dimensional. Those are one-dimensional objects. So before diving too deep into the general statement of the generalized Stokes theorem or this fundamental theorem of multivariable calculus, we do have to establish a single definition of a single integral, and that's going to be the one that kind of we can base everything else off of. So in terms of this integral here, what we're defining is the n-volume integral, and this is the integral specifically over one very specific kind of differential n form. It's not over general differential n forms, but a very specific differential n form, the n form comprised of the scalar value 1 times dx1 wedge dx2 wedge dot 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 wedge dxn in n-dimensional ambient space. So this is kind of saying the perfect n form possible. Of course, an n form in n-dimensional space can only be some scalar field multiplied by this particular wedge, but we're just going to let that scalar field be constantly 1, and we are going to define, here I'm defining the integral to simply be the actual n volume of the domain omega. So we're going to assume for now we know how to calculate this by other means. I'll say compute this, maybe geometrically. Eventually we'll learn how to compute it using calculus, but for now let's just assume we can compute it by some other means. We're going to get the n volume of the domain omega. So that's just going to be the definition of this particular n form, and we're going to need it kind of to see how the generalized Stokes theorem gets proven. So that's why I've included that here. That's the only one we'll have to work with. And I do have the remark here which refers to the superscripts starting with 1 to perfectly ascending up to n. Because of the way wedge products work, if I swapped any of those around, I would pick up a negative sign, right? If I swapped any of the differentials around, I'd get some negative signs. Of course, they would alternate between plus and minus, depending on how many you decide to swap around. But in particular, the order that just goes in the order 1 up to n is going to be the one of positive n volume. So let's look at some examples of cases where we can actually just compute these volumes using geometry instead of necessarily calculus. So here I have a domain omega, which is defined to be the x values in R1, right, one-dimensional space, where x values are between -3 and 5, or in other words, this is the open interval from -3 to 5, and I'm defining this integral to be the integral over the interval 0 to 5, or in other words, I'm defining, because it's just a dx here, and that's properly ordered, I didn't really have a choice how to order that one, just dx, we're going to define it to be the one volume, or equivalently the length of the domain -3 to 5, which we know how to compute lengths. You take the upper bound minus the lower bound, and we get 8. 8 is our one volume, or our length of this domain, or equivalently, that's how we define the value of this integral. Similarly, in two-dimensional space, I have this omega here, which I'm defining as the two-dimensional points which satisfy x squared plus y squared is less than 4, or equivalently, you could recognize this as the ball of radius 2 centered at 0, 0, right? So I can phrase this like that, and this ball is filled in. I should have given myself dotted lines on the outside because it is an open set, but the volume here would just be the area, so the 2 volume equals the area, and if this happens to have radius 2, then the area of a circle of radius 2 is pi times 2 squared, also known as 4 pi. So we just define the integral over the differential 2 form. 2 form is important because that's an R2. That's a 2 form, and then my order, the natural ordering of x and y is that x comes first. So we want to make sure that ordering of the wedge product is correct, but that integral then just gets defined as the 2 volume, or the area of this circle, which we know is 4 pi. In the event that I put a dy wedge a dx, we just have to play the game where those would get swapped at the cost of a negative sign, and so you pick up negative 4 pi for the value of this integral, where I've just kind of swapped around the differential form. And this is, you can think about this as equivalently as swapping the actual endpoints of an interval. That's really what's happening when we're swapping these differential forms around as well. There's an orientation baked into everything. We also have a case in 3 dimensions. This one's going to look a little bit trickier to everybody, I suspect. So we have omega here. It's the 3-dimensional points which satisfy x squared plus z squared is less than 9, and also that y is between -2 and 2. And to try to make a little bit more sense of what this actually is, let's forget about me actually describing it there. Let's see if we can come to a conclusion on what it looks like independent of my description. This first inequality looks like the circle of radius 3 centered at 0, 0. And the second one looks like the interval -2 to 2. And if we think about the variables that are involved in each of these cases, this is in the x and z directions. So we have this circle in the x and z directions, and we have an interval in the y direction. And now if I think about plotting, what would that look like? So maybe in my x and z directions, I have the circle. And then in the y direction, I'm going to extend out to 2 units in the y direction and 2 units in the negative y direction. And so what we end up seeing here is, of course, a cylinder where the that's kind of pointing out towards us. So if we can start to read what I've covered up, a cylinder of radius 3, so that's, it's my circular term, has radius 3, aligned along the y-axis between -2 and 2. So we can calculate the volume, the 3 volume, which is regular volume, of this cylinder. How would we do that? Well, we'd calculate the volume of the face of the cylinder. That's just going to be pi r squared, so 9 pi, and then we'll take the face of the cylinder and draw it upon the length. And what is the length of this interval, -2 to 2? That would have a total length of 4, so we'll multiply that by 4 and get 36 pi for the volume of that cylinder. So we're just going to define the dx, wedge dy, wedge dz integral over this domain to be the 3 volume of that cylinder to be 36. And of course, if we swapped some of these differentials around, we would have to pay the price of a minus sign to swap those two. So there's my minus sign. We would say that that volume is -36. And of course, in this last case as well, if I've got dz, dy, dx, I'm going to want to reorient this to an x, a y, and a z. So I will have to move z over at the cost of a minus sign. Now I have dy, dz. I'll have to move z over at the cost of another minus sign. And I'll have dy, dx, dz. And I'll have to move x backwards at the cost of a minus sign. So I'll get a third minus sign there. And I'll still call that -36 pi because 3 copies of a minus sign. It's just good to keep in mind if those terms switch their orientation to add your correct minus signs in. And now we can actually look back towards defining a fundamental theorem of multivariable calculus. So I just want to set us up here for how we maybe interpret the fundamental theorem of calculus that we use all the time, the one-dimensional version, and see what it looks like in terms of differential form. So I'm actually going to go to the bottom of the screen here and look approximately at this statement. Because what is this statement saying? It's saying, hey, if we think about a one-dimensional integral, where everything inside the integral really looks like f times dx, this is a differential one form. And it's integrated over a domain. We know that the fundamental theorem of calculus says that differential one form integrated over the domain can be computed by finding the antiderivative, but in fact, in our modern language, we can call this the primitive. And if it was originally differential one form, the primitive of the one form will be a 0 form. We have a primitive 0 form that's now evaluated on the boundary, and really there's an orientation to the boundary. Let's say evaluated on the oriented boundary of the domain. Because why is it evaluated on the oriented boundary? Well, you give the upper bound priority and call that term positive, and then on the lower bound, because it's oriented correctly, you call the lower bound term negative. So you have the upper bound minus the lower bound. So there's some orientation on the boundary. But that's really what this one-dimensional fundamental theorem is saying. You've got a differential one form that you find the primitive of, and then you evaluate the primitive on the boundary with a specific orientation. We're going to see if we can get the exact same thing in higher dimensions. And of course, we do get the exact same thing in higher dimensions. Here's our generalized Stokes theorem that you actually know how to understand now. Suppose we have ourselves a differential K form, and we have a domain which is smooth and orientable. That just means there's some natural directionality to it. So in higher dimensions, we just describe x, y, z as the orientation. That's the one that we've decided on in 3 dimensions, or x and y in 2 dimensions. Or if you're enumerating your variables, superscripts 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So some orientation on that domain. And if we're going to integrate the derivative of this differential form, this is the exterior derivative of that differential form over the oriented domain, the generalized Stokes theorem says that that integral has to be equal to actually the integral over the boundary of the domain. You get to drop the exterior derivative, so lose exterior derivative. Now, the only reason I've introduced it this way, this looks a little less like a regular fundamental theorem, maybe a little bit more like the integral of d dx of f dx equals f of x. It looks a little bit more like that one, plus c, I suppose, because we've got the d on the left-hand side and no d on the right-hand side. But this is actually the way the generalized Stokes theorem happens to be phrased in like most advanced calculus textbooks. So that's why I introduced this one first, even though the second one that I'm going to talk about soon is really the one that looks a little bit more similar to this one-dimensional version I just described. So you could either think about it as, hey, if I'm taking an exterior derivative and then evaluating over a domain, I can just drop the exterior derivative and then evaluate over the boundary of the domain. Or in the context of what we're used to, fundamental theorem of calculus, we can say, hey, if I'm going to integrate a k+1 form, so suppose f is a k+1 form, and moreover, suppose it's exact, so that's pretty darn important here, because without knowing that it's exact, and thanks to Poincaré's lemma, equivalently closed, at least in n-dimensional Euclidean space, we know a primitive exists so long as it's actually closed. So that's gonna be strong enough to give us some capital F, which will be a K form. And what the generalized Stokes theorem says is, hey, the integral over the domain of the exact differential form is equal to the integral over the boundary of the domain of its primitive. So I'm just going to read that out, what I have here. The integral of a function over a region is equal to its primitive evaluated on the boundary of that region. That's really what the generalized Stokes theorem is trying to say, and specifically with this function, most often we think about it as a differential form. And the primitive, of course, can only exist if f is closed. And so we do require that it's a closed or an exact differential form for the Stokes theorem to apply. So we're going to go through a really brief heuristic argument. Heuristic means like intuitionistic. Why should this make sense with our knowledge of differential forms? We're not going to get like a complete proof, and you can look those up elsewhere. They're pretty complicated, but the heuristic argument is pretty good. I think this is a pretty good argument for why we should expect this to be true. So we're going to try to argue why this second statement of the generalized Stokes theorem should be true. Why should the integral of a differential form over a domain be equal to the integral over the boundary of its primitive? Well, we're first going to recognize that it only makes sense if that is a closed differential form, because closed will ensure that our primitive exists. But even stronger than that, closed is going to tell us that the exterior derivative of that differential form is 0. And that's very important actually for the proof, because if we know the exterior derivative of f happens to be 0, then let's think about what the exterior derivative means. This is computing the infinitesimal change of that differential form over an infinitesimally small region. So it's saying over a small region, the change in our form is 0. And how can we see that visually? If we plot a differential form as a vector field, remember differentials are vectors and so are wedge products, so we can plot differential forms as vector fields. This, of course, is just a two-dimensional vector field. Here is a closed form that I've provided. And let's zoom in on the top right of this closed form. And so you think about what's actually happening with this zooming. This corner is becoming that corner. This corner is becoming that corner. This corner is becoming that corner. And this corner is becoming that corner. So we've zoomed in a little bit. And then we're going to zoom in again to the center. When we zoom in again, this corner is going to become that corner, this corner is going to become that corner, this corner is going to become that corner, this corner is going to become that corner. So we're zooming in again, blowing it up, and then zooming in one more time. Notice at each step of me zooming in on this vector field, the vector field is getting closer and closer to a constant vector field. If we look at this final vector field here, all those vectors look almost the exact same. They really are very similar. They're all pointing in the same direction. They've got pretty similar lengths going on. So basically, you zoom in enough, you recover zooming in enough to a closed differential form, makes everything look constant. I'll just say everything look the same. So that's what's nice about these closed differential forms. Everything looks the same when you zoom in enough. But what that means about our theorem is that we can get away, at least for now, we're going to try to get away with just saying, hey, up to like giving myself the ability to zoom in, I'm going to prove this generalized Stokes theorem for constant differential forms. So I know if I zoom in enough, I'll get a constant form as long as I start with a closed form. And so let's just assume that I've already zoomed in and then just work with constant differential forms. Okay, so then what does a constant differential form look like? Well, if we're working with k-forms, a constant, I'll labeled it with a c here, a constant differential form is just literally a constant, ci, some constant scalar, multiplying a k-form. Here's k-form, right? Any k-form. Now, we could have multiple k-forms added together, right? Because they could all be pointing in different directions, right? If it was just a single k-form, that would say that each of these constant vectors were all pointing just purely horizontally or something, right? But you can have some linear combination of the basis vectors. But basically what this is saying is this is a constant linear combination of basis vectors. And it's pretty easy to actually find a primitive of constant differential forms. You can actually compute them quite easily. Now, primitives are not unique, so I've just provided a single primitive here. You can work with any primitive, but I've just found a single one that I'm calling capital C. Turns out all I have to do to get a primitive is I take this dxi and the wedge that comes by it, and I'm just going to remove the wedge, and I'm going to remove the d. And so I'm just going to call it ci xi1. And so now that's going to be my, well, what is the integral of a constant? This is a linear differential form. But it's also a differential, k minus 1 form. So because it's a primitive of our earlier k form. So I found a primitive of my k form, very specific primitive, just by by direct computation. You could find out if you take the exterior derivative of capital C, you will get lowercase c. That's not really the big deal here, but I do show that, where you take the exterior derivative of big C to get lowercase c. What we do care about is computing, because Stokes' theorem cares about computing the integral of the differential form over the domain, as well as the integral of its primitive over the boundary. So big question now, can we show these are equal? Hopefully the answer is yes. And to do so, let's just recall how integrals work. Well, my integral can certainly pass over the summation, and actually can certainly pass through this little constant. So this is where those volume integrals are actually going to play a pretty big role. This is why we defined the volume integral. Because you'll see now, what is this integral reduced to? It's just an integral of omega over one of these volume forms, right? The coefficient is constantly 1 against those. So we're thinking about that truly as just the k volume. Okay, we do have to take care of the I directions. It's the k volume within the I directions of omega. So that's what we have there as a volume. Of course, we're adding maybe a lot of these volumes together. What we have on the boundary here, if I compute the boundary of the primitive, I can still take my integral and I can pull that integral through to the constant terms. I've got a little typo here. This should, of course, be that. But I can pull the integral through the constant terms, and now we have this integral, which actually does not look like a volume integral. No longer looks like a volume integral. But we will show that it still computes volume. Still computes the k volume. And that's what's going to get everything to work out for us, because notice that, these terms out front are exactly the same. These terms right here and here are exactly the same in both cases. So as long as I can guarantee that these integrals are exactly the same, then I should be good. So let's try to compare those integrals together and see if they compute the same kind of volumeness of that omega. To do that, it gets a little bit tricky. I don't think I want to talk through all of this this jargon here. What I would rather do is think about what these integrals are actually computing. This is a k form. In other words, it's a wedge product of differentials, right? Wedge product of k differentials. And so it's a k dimensional. Well, really, because it's just dx in each case, a cube, right? Unit cube. It's a k-dimensional unit cube of infinitesimal size. And what we have on the right-hand side here, this is a k minus 1 dimensional, I'll call it a unit square. It's one of the surfaces, right? So this is a surface of the unit cube. of infinitesimal size. And that surface of the unit cube of infinitesimal size is being scaled by xi1 over this boundary of the domain. So let's see what that actually looks like visually, and then hopefully you can believe me about why this would work out. So visually, here's a three-dimensional object that I've provided, and I'm going to represent that three-dimensional object as a combination of infinitely many unit cubes, right? These are the infinitely many, infinitely small. Okay, they're finitely small in my image, but of course, if I drew them infinitely small, you wouldn't be able to see them. So infinitely many, infinitely small unit cubes which tile the volume. And then we add all of them up, gives total volume. This is the volume integral. If I just integrated dx, dy, dz over omega, I get the total volume. This volume integral that I started with. But now let's think about what the other one, what did this other side say? Looking at the face, this is the face of the unit cube, and then the face is being scaled by one dimension, one of the other, whichever dimension I peeled off, I'm scaling the face of the unit cubes. What does that look like? It looks like this. Now what is going on here is each of these are all like columns in the z direction with faces agreeing with dx wedge dy. So if I look at every single tiny little face at the edge of these columns, those are all little tiny squares. They're unit squares, right? And then the entire unit square is kind of dragged down through the shape by the action of this multiplicative z. So it's the action of the multiplicative z that got peeled off, right? Because z is multiplying that little unit square in the z direction to give me this very large column. So this is really the integral of z times dx wedge dy over the boundary of the domain. Why is it just over the boundary? Well, let's ask where dx wedge dy actually exists on this plot. It only exists up here, right? The face of these columns only exists at the top, and it only exists at the bottom of this shape. It doesn't exist on the interior, right? Notice, I'll say notice no unit cubes surfaces within the interior of this shape. And yet, if I added everything together, I'm still recovering the same volume, right? Added together recovers the same volume. Okay, so that is me completing all of this jargon. If you want to read through the jargon, you can try to figure it out. But that's me saying, here's me tiling that shape just with infinitesimal unit cubes, and then this is me tiling the shape with columns whose faces are the faces, a specific face of those unit cubes, and then the column extends in the remaining direction. And they end up producing the exact same volume, which is why the generalized Stokes theorem should hold true for constant differential forms. Now, in terms of non-constant differential forms, we ran this process of zooming in to get a constant differential form. How could we make the argument that it's still going to hold on the wider space? Well, what I'm going to do is I'm going to tile all of the differential form using these squares. You can imagine I can still tile on the bigger stage too, using these squares, and then again on the bigger stage using squares. Basically, if I divide everything into infinitely many of these big square tiles, I will be able to show that the integrals are going to cancel along these boundaries of the tiles, and they'll remain along the true overall boundaries of these tiles, which means as you grow larger and larger, kind of this notion of an integral along the boundary itself survives, and everywhere that we try to place tiles next to each other, the integrals are just going to cancel along these overlaps when we place tiles next to each other. So we're just going to tile all of space with increasingly smaller tiles where the edges of those increasingly smaller tiles are canceling. So how does this actually work? We have to keep in mind this idea of an orientation. And of course you would orient, right? If I gave myself the x-axis here, you would call the left-hand side x min and then the right-hand side x max. And so you have this notion that x min moves toward x max. And also, if you preference x over y, then you choose to orient in the x direction first and then in the y direction second. So if you preference x over y, now you go from y min to y max. You can start to see we've provided an orientation to the boundary of our square. And if I continue this orientation so that it's smooth, I pick up a counterclockwise rotation along the boundary of my square. And so it turns out the orientation on boundaries, at least in 2 dimensions, recovers counterclockwise-ness. And what's going to happen if I go ahead and tile that square into 4 smaller squares and repeat my counterclockwise-ness on each of the smaller tiles is, here's my outer counterclockwise-ness. But on each of the smaller tiles, I'm also drawing counterclockwise-ness. So that's going to give me a left pointing x value on the bottom right tile, but a right pointing x value on the top right tile. I'll get a left here and a right there as well. And I will get an up here as well as a down here, and an up here as well as a down here. And what's going to happen is all of these interiors, because you have exactly one orientation in one direction and one orientation in the other, those are always going to cross each other out. And it's only the true boundary orientation that remains when you integrate over this larger region. And this is going to be true no matter how I decide to tile space. So what I've brought here is a much larger tiling of all of space. You can see no matter how I set things up, as long as I run my boundaries in a counterclockwise manner, one side will always point in one direction, and then the overlapping side will always point in the other direction. And so everything cancels no matter how these boundaries work out, how I tile my space, everything's always going to cancel, and the only boundary that you're actually left with over all of space is the overall boundary. And so you can get away with assuming everything is constant because of the closedness of the differential form, and then you can kind of grow the result from the constant case of the differential forms, which we saw from tiling that volume space. You can kind of grow that to all of space. So really, it's a very fascinating result that we have here. And I'm just going to finish by saying that really computing either side of these generalized Stokes theorems in generality is going to require actually, calculating integrals in multiple dimensions. So that kind of will be our job for the rest of the semester. It's actually learning how to compute these. You probably believe me, it's quite hard to do. So it's a very hard thing to do for the rest of this semester, unfortunately. So we're going to start learning about how to compute, set up, and interpret integrals in higher dimensions for the rest of the time. We're going to start out with line integrals and their respective fundamental theorem in the next video. I'll see you then. Bye.